So here we go with chapter 19. The unit or the chapter in the textbook refers to as a history of life. This is a sort of a condensed version of that. I don't have 4.6 billion years of time, but we sure as hell have 4.6 billion days of quarantine here, it appears. So paleontology gives us our fossil studies that we remember are very, very important to the work of evolutionary biologists because it actually gives us artifacts to study, right? And we can make inferences then based upon what past organisms were like. You know the term extinct. What might be new to you sophomores is the term extant, which means still living. So we have to consider those terms when we're comparing living creatures to their non-living counterparts in the evolutionary process. But for now, I just want you to watch actual footage of when the dinosaurs experienced a meteorite that changed Earth's history forever. Again, this is actual footage. Bring on the actual footage. As you can see, it happened in slow motion. And our dinosaur our friends, our pals, had a sense of humor. So that actual footage makes it real. So how do fossils form? Obviously, something has to die, or it can be fossilized while it's dying if it gets covered up pretty rapidly, right? So we know that fossils come in all shapes and sizes, microscopic. Yes, we do find microscopic fossils. They're just a little bit more difficult unless you know where to look, and even then, it's still more difficult. But we do find fossilized eggs or footprints, poop, whatever. Sedimentary rock, and the process is pretty perfect. In terms of sedimentation, a fossil will have died at some point, become covered in sediment, and then compressed over time, preserving its remains in a pretty decent form. Obviously, varying levels of this are possible. Talking about volcanic ash, amber. So the way that it died, how it became fossilized, are very, very important to what's left millions of years later, how it's been revealed, the environment that it was becoming fossilized in, whether it was very organic and warm and wet versus inorganic and dry. So it's very, very different. So we do know that great fossils do exist. Finding them can be somewhat accidental, but we do know that they exist. Right? So what we do with this is we have to interpret it. Okay? Geologic forces, I mean erosion of wind, rain, Earth tectonic movements, any number of possibilities, reveal those fossils. And then we're going to date them in one of two ways. Their age relative to the fossils around them, or more scientifically, the radioactive age. So in relative dating, we just take the layers and we know the age of these layers because they exist all over the Earth. And the lower something is buried, the older it is. It becomes younger as we move near the surface because the presumption is that the top surfaces are the newest and the bottom surfaces are the oldest. So anything found in that layer down below would be older than anything found above it. And that gives us the opportunity to talk about what index fossils are, which are fossils that were widespread geographically and only live for a short period of time. So if you find them, you know that they were living in a very brief period of time, and that layer that they're living in is the same age across the planet. If they live for a longer period of time, that gives you these expanses of saying, well, it could be from this million years old to this tens of millions of years old. Whereas if it only lived for a million or two or less than 10 million years, that's still a relatively accurate description of the age of that layer. So if we look here, fossil A can be found here, here, and not over here, which means that might not have lived over in this region, okay? But something that lived across all three would be of a very interesting concern to us because that could serve as an index fossil. We know the age of that layer, anything above it is younger and anything below it is older. Then we can talk about radioactive. It's sometimes called radiometric dating. So we use radioactive elements and they decay at a steady rate. So there's some chemistry and physics here that we don't need to go into in this type of format with this video, but a half-life then becomes the length of time that half of the element takes to decay. So carbon-12 is non-radioactive, and carbon-14 is a radioactive isotope of carbon-12. It decays over a known period of time. So what we do is we compare those two. We take the known value of 12, and the difference between 12 and 14 tells us how much of the carbon-14 has decayed, and that gives us a known number of years because we have a graph that tells us how long it takes carbon-14 to decay. In this case over here, we're actually looking at potassium, which has a much longer half-life of 1.2 billion years. But what we're going to find is the same situation where half of it decays over a period of time, and that's called its half-life. So if we look at the top of the graph, there's good ACT prep for you too. So here's our time, how long it takes, and here's the fraction remaining of potassium 40. So this represents 100% of the potassium. Okay, one half-life, which is found here, is going to be the amount of time it takes for half of it to decay. In this case, 1.26 billion years. So to lose half of half, you end up with a quarter of the overall, and that's two half-lives found here, which should be in the order of 2.62 billion years. Okay, 2.52 billion years. All right, and then this one would be 1.26 billion years more. So if we find this amount, we can say that's 3/4 of what's remaining, and we know that that's half of a half-life, so this would be 1.26 billion years divided by 2, and you can understand the math from there. And that's what allows us to come up with this geographic time scale, geologic time scale, and it's skewed because down here we've got the first 4 billion years approximately of Earth's existence, and from this point farther up to here we end up with the last 0.6 or 500 to 600 million years where most events occurred. It's not to say that nothing good happened down here, because we've got eukaryotic origins, we've got the origin of oxygenation, and the origin of sexual reproduction. Those three events right there were huge, leading to the diversity that occurred all through here and these major changes that occurred at these mass extinction points. All right? At this time, I would ask you at home to go ahead and do this activity. I just clicked on Interactive Earth Timeline. Yeah, so for the purposes of time, just take yourself through this, and it's clickable. We can move around it and close this guy and then click on different events. Let's say I'll maximize it here. But you can play yourself through it. So it's a neat thing that you can click on if you're interested. I know you have lots of time, so just get into it. And then you're starting to see down, I don't know if I can show you. Yeah, I can't really highlight this guy, but if you see in the lower left-hand side, you see eukarya branching off. And let's get back through here. Archaea, bacteria, eukarya branching off of it there. And then you see the different groups out here, the major groups. And this is almost right in line with the 6 major kingdoms, but it's not quite. So definitely take yourself through this and enjoy that with your curiosity. Okay. So what I'd like to do is put this time period into a reference point that we can kind of understand exactly how this is going on. So what we're going to do here, this is actually a 24-hour clock, and that's somewhat misleading because we're used to half the day being down there midway through. So this point here is actually 6 hours, 12, 18, and then 24 hours throughout the day. So a 24-hour period if we start at midnight. All right, so we don't see, there's atmospheric changes that happen here. Like Earth has to cool enough for water to form. Uh, well, before that, liquid rock had to cool to solid rock at around, I don't have to always fact check this, like 2,500 degrees Fahrenheit. So Earth's atmosphere is very, very hot. And then somewhere in here, water forms. So that means the atmosphere is less than 212 degrees. But right around a 25% point in time, we see the first living cells. And again, that is the evidence of the first living cells. So what we can do is say that each of these periods is 1.5 billion years. 1.15. So that makes this about crap, give me this back. This is around 3.45 billion years ago. This is around 2.3. And this is around 1.15 billion years ago. So at 3.5, we call it around 3.5, is the first evidence of living cells, which is here. And that's nearly 6 hours throughout the day. It's not until 8 hours of the day have passed that we see photosynthesis. I'm just trying to underline that there for you. Eukaryotic cells have only been here for half of Earth's history, and then multicellularity for only a quarter of Earth's history. And then somewhere in here, right after this, is when sexual reproduction begins. And you notice that the major events all happened here, and that's all within the last 3 hours of the day. And right at the very end of it, and this is awesome, human history is just over 1 minute of 24 hours of Earth's history. That's a very, very brief period of time. And modern humans are considered to be around 150 to 200,000 years old. So while we've been here for a great deal of human time, geological time, we pale in comparison. And then what you have to consider while this is occurring is what Earth looked like. Okay, so right here at 225, we're talking in the neighborhood of, let's see, peeping this out a little bit, somewhere right in here is what you guys think of Pangea. All right, that's when Pangea started to split apart. So all throughout this period, from here to here, Earth moved, and that's what the video is kind of about. We watch an animation on this. It's important to note that Earth's location, where we are today, the way we think of the Earth, is not what it was 225 million years ago. And then it started to migrate into its form today. And when this dinosaur extinction, which, if you look at that, guys, 21 minutes of a 24-hour day, 21 minutes it goes when dinosaurs went extinct. So very, very, very near us is their extinction. But they began on Earth, what's that, an hour and 15 minutes prior to the period of time that we live in now, which that's a decent amount, 1/24 thereabouts, okay, a little bit less than that. So important to note these changes that occur. Now, what I've done is I've pulled up the YouTube page. I want you guys to watch a video. So let's see if I click on this one. Good. Now this one, I'm going to pause it real quick. I want y'all to watch this one. It's open. It's open to everybody. I'll let that fly. I paused it. Watch this one. It's a 60-second video. It's pretty dramatic. Pause. Just pause. Good. All right. So this one's pretty neat because it gives you the history, and I want you to pay attention to the clock in the lower right-hand corner to see that there's huge periods of time where nothing actually happened. All right. So that's pretty awesome. So watch this video on your own. And the other one presents somewhat of a challenge. The continental drift video, Rise of the Continents. The one that I'm supposed to show you in class is this one. It's called Rise of the Continents, Eurasia. You can see in the search bar up there. Now, if you have a YouTube account, you can buy this. It's $3. I can't make it public for you because I don't own it, but we would watch it in class. I would tell you that it's an interesting video. I know you guys are doing lots of screen time right now. So it really talks about some parallels between evolutionary origins of creatures that live on different continents and how we would find fossils of similar creatures on different continents. Well, that's a push towards plate tectonics and and how when these creatures evolved, the continents were much closer, if not touching each other. And that's what this one's about. It's a full series. It's only one episode. But if you have $3 and you want to buy it, it's not going to be a waste of your money. All right, and then this one will be your homework assignment for this video here, which is probably near, yep, right there, 15 minutes. So, all right, I'm going to shut it down now and do this homework assignment and start working on your study guide. Later.